Good. So today is March 27th, Wednesday. We finished chapter 20 and 21. Remember that we're going to go back to chapter 20 to cover alternating circuit. And why is that? Why I didn't do that before? I didn't do that before because we need the material of chapter 21 that we just finished. Wait a minute. No. After chapter 22, not chapter 21, it's chapter 22. Okay, we didn't cover alternating circuit yet because we need the material from chapter 22 to explain how alternating circuits work and how we can get us a power supply for that will produce this alternating circuit. Okay, so it's after chapter 22. So what else we have here? I corrected lab 2, the report for lab 2, and posted in your group folder. Okay, I had a problem last time because there was a bug in my computer program. I couldn't get it corrected earlier, but I managed to do that. And remember, right? We also cut short our class last time. What happened last time is that the internet cable outside my apartment was too low in the street, and a truck came by and yanked it out, and that's what caused the problem last time. Okay, but now it's already fixed. Hopefully, that's not going to happen again. And let's take a look at the syllabus so we can locate ourselves where we are. Okay, we did it. We are writing here. Week number 8, 27 of March. Let's write that down here. Wednesday, week number 8. Okay, week number 8. Going back to this syllabus, I will cover chapter 22 in the first hour. Hopefully, we're gonna get ahead big time here. And let's see if we get more students coming in or not. If you don't get many students coming in, we just continue with the lecture, right? So maybe that would be better if you do that, so the other students are not punished for the lab reports. And though we have a spring break, then we're gonna have our Monday class, and after the spring break, the Wednesday after the spring break, we're gonna have exam number 2. It's gonna be, I decided that's gonna be just chapters 20 and 21. Okay, more students coming. Go Sky. Okay, and 2021 for exam number 2. And the material is this one that you see right in here. Right in here, okay? Chapter 20. Doesn't show up. This one doesn't show up in chapter 20. Let me just, I'm gonna just erase it so you don't get confused, right? Section 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. For chapter 20, sections 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's see. I'm gonna put it out. Alternating circuit. We'll cover it after chapter 10. Let's put it this way, and will be part of exam 3. This section. Okay. Don't worry about. It's not gonna be in exam 2. It's gonna be exam 3. Let me emphasize that. What else you have to worry about this coming exam? Labs 1 and 2. And try to review the notes and videos, YouTube videos, right, that I showed to you. They are very helpful. They are very helpful. So the main idea here is, of this chapter is just electric circuits, how you have current flowing, right? How you have resistors in there, have resistors that can be connected in series and in parallel. And then here in this case, we are working only with what we call direct current. Current that flows in only one direction. Current that flows in only one direction, okay? That's what this chapter is all about. We're not doing section 20.9. Okay. But then what's the next chapter is all about? The next chapter, this chapter tell us how magnetic fields are generated and how magnetic fields are generated. And you need a current. You need a current flow. It's the current that generate a magnetic field. That was a law that was introduced in physics. Okay. And now we can continue with chapter 22. We can continue with chapter 22. This is the material. Material for exam 2. Go. Exam 2 material. Okay. How am I going to do that? I'm going to put a page break here. Right? Let's put a page break here. Chapter 22. Not part of exam 2, okay? Not going to be part of exam 2. Central idea of chapter 22, okay? How to generate a current in a closed circuit without a power supply. That's the central idea of chapter 22. Okay? That's the central idea of chapter 22. And I showed to you illustrations and also videos, right, on how that happens. We go, and that's also called Faraday's law. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. I'm going to repeat the formulas here. The law of physics. Here you go. That's Faraday's law of electromagnetic induction. We are almost there with every law that we have in physics, almost there. And I'm going to copy, right? Here you go. What I want to do, I want to put this magnetic force law at the end, right here. Faraday's law of electromagnetic induction. Like that. Okay. 5 laws. Those 4 laws that you see here are the laws that we call are the above 4 laws. It's like equations are usually referred as Maxwell's equations, the equations of Maxwell's equation. That's not exactly Maxwell's equation, but it's close enough. Okay. We are going to, and later on, we are going to adjust this equation here. So you have it, we have it formulated in the right way. okay? Later on, you don't have to worry about that now. At this point in time, you have to worry about this one right here, okay? Don't forget here, oh, and I'm gonna do like that. And then there's a very important difference between, don't forget, this is the magnetic flux, right? But it's the magnetic flux. Here too is a magnetic flux. But I'm going to emphasize here that this magnetic flux is the magnetic flux. Very important. Here you go. Closed surface. Through a closed surface. And oh no, sorry. It's not a closed surface. It's a closed pass. And okay, so I'm mixing up here. It's this one right here. Yeah, but close the surface. And I'm going to abbreviate the closed surface as a little o. Okay? Magnetic flux through a closed surface. Here too, we are going to have a flux, but it's not going to be a magnetic flux, it's going to be an electric flux through a closed surface. Gauss's law for electricity, Gauss's law for magnetism. Okay, this one that you see right in here is Ampere's law. Ampere's law. Now, why am I doing that? You know, because there's a difference between this magnetic flux here. If this magnetic flux is through a closed surface, this magnetic flux that you see here is not going to be through a closed surface. Let's see. Let me put the notation a different way. Closed surface, like that. Closed surface, closed surface. Here is going to be a magnetic flux through an open surface. Okay? Open surface. At this point, you should already know how to calculate the flux at either electric or magnetic through any surface, open or closed. Okay? So that's the important difference between this magnetic flux and this other magnetic flux that you see here. That's the important difference. And finally, we have this magnetic force law. And okay, we saw that and different ways of generating a current through a closed circuit. Okay, and now what we are going to find out now, I'm going to show you how we find the direction of the induced current in this circuit. Okay, that's how the first thing here, how to find the direction and how to find the direction of the induced current through a closed circuit. That's called Lenz's law. Okay, and it's spelled out in chapter 22.5. Okay. And going back to our, and don't forget, this thing here can also be written as if you have a resistor, right? If you have a resistor in your circuit, like that. This law reduced to something like that. That's 4 ohmic circuits. 4 ohmic circuits. The above law reduces to equal Ri. Open surface, open surface. Okay, how do we find the direction of the current, of the induced current through a closed circuit? Well, you have to look at this sign here. Okay, you have to look at this sign here. And have to look at this sign. So if, let's say, let's do one by one. If the magnetic flux is increasing, okay, comma, then the direction of, then here you go, the negative sign of the equation states that the direction of the current in the induced circuit will be contrary to the magnetic field. Okay? That's how you find out the direction of the induced current. So here you go. If the magnetic flux is increasing, here you go. And now I'm gonna put it decreasing. Then the negative sign of the equation states that the direction of the current will be contrary, will be in the direction, contrary to, in the direction of the magnetic field. Okay. I cannot prove that mathematically because this thing is a law. And now I'm just telling you how you interpret this law. I'm going to do some examples. Okay, examples. Here you go. We have a loop of conducting wire subject to a magnetic field that changes in time. Okay, so here you go. Here's the magnetic field that changes in time into the board. Too many magnetic fields here, right? Make it look good. Let's say, make it look good. Magnetic field is in the board. I didn't say yet how the magnetic field is changing, if it's increasing or decreasing. So here you go. So let's say that this magnetic field is increasing as time goes by, okay? The change in magnetic field in with time has a positive sign. Delta B over delta T is greater than 0. So that's one example. And here you go. Okay. So what's going to happen? This magnetic field will change, is changing as time goes by, and this magnetic field is going to affect the magnetic flux as well, right? A changing magnetic field results in a changing magnetic flux, and a changing magnetic flux is going to induce a current in the circuit. Now the question is, in which direction? Okay, well, if the magnetic field is pointing into the board and the magnetic flux or magnetic field are increasing, the resulting current must be induced in a direction contrary to the magnetic field according to the right-hand rule. Okay? And that's what I have to add here. If the magnetic flux is increasing, then the negative sign of the equation states that the direction of the current in the induced circuit will be contrary to the magnetic field according to the right-hand rule. Okay? So this field is increasing. Consequently, the current must rotate contrary to the direction of the magnetic field, which is going to be, counterclockwise. Okay. Counterclockwise. Here is another, way of applying Lenz's law. Okay, since the external magnetic field is increasing, so this external magnetic field is going to induce a current that has a magnetic field associated with the current. Okay, and this induced magnetic field associated with the induced current is going to point contrary to the external magnetic field. That, what does it mean? It means that the induced current is going to rotate counterclockwise in the circuit. Okay, like that. Okay, so according to the illustration in the class, right? Example, consider a closed circuit in the plane of the screen, right? Of the computer screen. Of the computer screen. The circuit is subjected to a magnetic field that points into the board. Okay. This magnetic field increases as time goes by. Okay. Find the direction of the induced current. Okay. Solution. Okay. 1. B field that changes in time implies a B flux, a magnetic flux that also changes in time. That also changes in time. 2. B field that increases in time, implies, a B flux. Let's say B field that changes in time implies B flux. B field that increases in time implies a B flux that also increases in time. Imply a B flux that also increases in time. Okay. I'll call that the external B flux. External field flux. Okay, external field flux. Okay. This external B flux that increases in time will induce a current that will have its own B field pointing in the direction that counters the increase of the external B flux. Okay. Using right-hand rule, we conclude that the induced current will flow in the counterclockwise direction. Okay, just like we have here in the drawing, counterclockwise direction. You know, the palm of your hand is rotating in the direction of the induced current, and the thumb must point in the direction of the induced magnetic field, right? Here is the external magnetic field, here is the induced magnetic field. So two different types of field here that you have to keep in mind. If the sign changes to negative, then the induced current must rotate in the other direction. Okay, now here you go, and that's what we have here. And less than 0, right? Less than 0. See now that the magnetic field associated with the induced current is pointing in the same direction as the external magnetic field, right? Consequently, the induced current must flow in the clockwise direction. Okay. Magnet at rest, remember that? Magnet at rest, nothing happens. No induced current. If we approach the magnet to the circuit, it means that the magnetic field is increasing, the magnetic flux is increasing, consequently the current must flow in this direction here, right? If we are withdrawing, then the current must flow in the other direction. Here is the motional electromotive force. A railroad, right? Railroad track, a bar connecting the two tracks, and then we connect a resistor right in here. This bar is moving from the left to the right, and on the top of that we have a magnetic field point into the board. Okay, that's what we call the motional magnetic field. Okay, because the area here of the circuit is increasing, it means the magnetic flux is also increasing. If the magnetic flux is also increasing, the induced magnetic field must be countered to the external magnetic field. If the induced magnetic field is coming out of the board, it means that the induced current is going to rotate in the counterclockwise direction. Okay, another example using the examples. Changing B field. Okay. The other one is going to be changing B field. Motional, we call that motional EMF. Consider a railroad track. Okay. A railroad with two parallel tracks, right? With two parallel tracks. Don't forget, those are made of conducting material. Put a bar across this track of length L, okay? And make it move with velocity V. Okay. Close the circuit at the other end, with a resistor R. Right? There you go. That is a B field pointing towards the plane of the screen. Paper, if you want, right? Find one, the initial, let's put one more thing here. Initial area of the circuit is A naught. Okay, let's put it this way. Find how the B flux changes with time. Okay. 2, the direction of the induced current. And 3, an equation for the induced current. Like that. So that's another example here. Example 1, example 2. Now we're getting the hands dirty here, right? Go. And then how the B flux changes with time. Okay, just like before, B field. B field, by the way, there is a uniform, I gotta put here, a uniform B field, okay? The field does not change in time in this case, okay? Does not change in time in this case. In this case. However, the area of the circuit does change in time, okay? Does change in time. Consequently, the B flux, the magnetic flux, the equation for the magnetic flux is the equation for the magnetic flux. You gotta remember, right? The equation for the magnetic flux. I'm gonna get here. Here you go. Don't forget this magnetic flux is an open surface. It's going to be, just the magnetic field times the area of the circuit. Okay? And what else? Oh. Because the B field is parallel to the area vector of the circuit, comma, there is no cosine theta term in the equation, okay? And then we can start writing down here. We already going back to the drawing, right in here. Here's the area. Let's say here's the area time t equal to 0. This is my A naught area. A naught area. Okay. The circuit is increasing according to VT. Okay. LVT is the increase in the area of this circuit. Make sense? A naught here. I'm gonna play the movie for you, right? Here you go. This, and I'm gonna put here time t equal to 0. Time t equal to 0. A equal to A naught. Area of the circuit is equal to A naught. I'm going to subscript. Right, and then a little bit later on, t greater than 0, A greater than A naught. Okay, so here go, this guy is gonna move a little bit to the right. Let me move that a little bit to the right, right? And now we have a different value for the area. Oh, and I'm even going to copy that and paste in there so you can see clearly that there was a change. Size and position, let's see, outline right in here. I want dashed, okay? Just to show you that there was the V velocity is right here. This displacement that you see from here to here. Let's see, this one right in here, boom. This one until here is going to be VT. This distance here I'm covering, I'm gonna put as being VT, right? The amount increase in the area is going to be it's going to be like that, B times A naught plus VT times L. Make sense? Right? VT times L. Here is what I call the delta A. Okay? I'm going to even emphasize that what we have here is A naught plus delta A. But delta A is given by VT, the linear displacement, times the size of the circuit, VTL. How the B field, B flux changes in time. We got it. We got the equation. Okay. Direction of induced current. Direction of induced current. Direction of induced current. Go back to the drawing. The direction of the induced current is obtained from the direction of the induced magnetic field. The induced magnetic field must counter the external magnetic field. Applying the right-hand rule, we get counterclockwise direction, right? So I'm going to repeat it here. See, solution. You want to put it A instead? Okay. Solution. Direction of induced current. No, counterclockwise. Let's put it this way. Right? Next, equation for the induced current. Equation for the induced current. And by the way, let's put it here, delta t, right? Would be better if you put delta t. Equation for the induced current is going to be what we saw before, right here. Even better, magnitude of the equation. I'm going to make it simpler. Magnitude equation for the magnitude of the induced current. Magnitude of the induced current. Magnitude, okay? That's the change that I made here. So it makes it easier for us to solve this problem. That's going to be the equation, right? But we are talking about the magnitude of the induced current. It's going to be like that. Okay. Since we are taking just the magnitude of the induced current, we don't need the negative sign in there. Change in magnetic flux is going to be the final magnetic flux. Now I'm going to erase that that part here just to simplify the notation. Final magnetic minus the initial magnetic flux. I don't need, let's see, why is this A here? This A is not supposed to be here. Okay. This A is not supposed to be there. And then we go ahead using the equation for the final and the initial. Okay. Final magnetic flux is this one that you see right here. Initial magnetic flux is this one here without the V delta T term. Without the V delta T L term, okay? Just this A naught that you see right here. And now see this term here cancels out with this term. And all that you get, oh my goodness, all that you get at the end is going to be this thing here, VB delta TL. Delta T cancels out with delta T. And we end up getting BVL. We didn't finish yet. We still have to write down in terms of the induced current, right? So we have to put a resistor downstairs. And that's what we get. BVL over R. Okay. That's the case of the motional EMF that we have right here. The book makes it slightly different. The book is combining, the Lorentz law in this case. Well, what's happening here? He did something else that I didn't do. Okay. Suppose that there is no conducting rail here in this drawing, and you have only this bar that is moving from the left to the right. If we apply Lorentz first law, right? V cross B, what's going to happen? We are going to have that the positive charges in this bar is going to move upwards, V cross B, okay? And then we are going to have a polarity here in this bar, positive at the top, negative in the bottom. If we close the circuit, what's going to happen? This bar is going to behave like a battery. It's going to behave like a power source. And then you're going to have a induced current in the circuit. That's another way of looking at the problem. You can look at this problem either in terms of Faraday's law or in terms of Lorentz force law. Okay? And VBL, see, we get exactly the same thing. Not this one right here. VBL. And then you have, you apply Ohm's law to this electric potential, that motive force, VBL divided by, the resistor. VBL divided by the resistor. That's an example in the book. Okay. That's a relatively strong field. Okay, 0.8 Tesla is a relatively strong field. Almost 1 Tesla. Okay. And that's what motional EMF is all about. Okay. Here is the chapter on the magnetic flux that shows you how to calculate the magnetic flux. At this point in time, you should know how to do that because you already know how to calculate the electric flux, right? The idea is the same. This is a sample case in which the area vector is parallel to the magnetic field. But things start to become a little bit more difficult when the area vector is not parallel to the magnetic field, when the area vector makes an angle. Okay? Here is the case of a uniform magnetic field making an angle phi with the area vector of this surface here. Okay? And it becomes even a little bit more complicated when you have something that is rotating about the magnetic field lines, which is, by the way, is the principle of the generator. That's where I stopped last time, right? Last time I was talking about that. So last time I was telling you, let's go back to the notes. Okay, last time I was telling you about the electric motor. Recall the electric motor, how it works, right? What if the field, if the circuit does not translate, but just rotates? What this rotates with respect the uniform magnetic field, right? Magnetic field. Okay, so that is the principle of the generator, which, by the way, is something I want to install here in my place. Whenever the electricity goes off, I just start my generator and continue teaching, right? And there's a nice thing about the generator. The generator is nothing but the inverse of an electric motor. Okay? So recall the principle of the electric motor, the principle of the in that simulation that you saw. And let's go there in that simulation too. Okay, in the case of the electric motor, we use an electric current. We input, right, as an input to the device, and the output becomes an oscillation or a rotation. So electric energy is converted into mechanical energy. That's how the electric motor works. Let's go back there. Let's see. Let's take a look at that simulation. Should look for that here. Let's see if I can find it. Okay, right in here, this guy. Better. Look back at the simulation we saw before. Look at the simulation we saw before. Like that. Okay? So that you should already know because we covered before. Okay, so we just pass a current through this. I'm going to decrease here. Let's see. Yeah, we're just passing a current here. And this current is generating a torque in this circuit that makes the circuit rotate, provided, of course, you invert the current at appropriate time. Okay? Here, the input is electric energy and the output is mechanical energy. The generator is exactly the opposite. Let's go back here and define it. Okay, mechanics, oscillation and waves. See, he has a bunch of simulations here. Direct electric motor. We want combinations with steam potentiometer, ohms law, generator. We want the generator. So look here how the generator works. The generator is exactly the opposite of the electric motor. You crank up the circuit manually or with a diesel engine, for instance, okay? Subject the circuit to a magnetic field, just like we did for the electric motor. And then what happens? Just by cranking up the current, you induce a current in the circuit. Okay? That's why we have this voltmeter here. Okay? And it's possible to see it right here. Let's see. In that illustration that you saw. Okay? Not here, the other way. Okay, right in here. Okay? So try to visualize this circuit rotating as time goes by. Let's see if I can. Here you go. The circuit is rotating, right? So you're going to have this picture. It's rotating about this axis. Okay? That's an instant later. Another instant a little bit later. You know, the plane of the circuit is off the plane of the board here, right? A little bit later, you know, the circuit is going to look like that, right? It's not that the circuit is deforming. No, the circuit is not deformed. The circuit is just rotating. Okay? And here you go. We are going to have a current that's going to be induced in a given direction. And then after that, you know, eventually this circuit is going to be exactly sideways. The magnetic flux is going to be zero because it's sideways compared to the magnetic field, right? So what's happening here? Right now, the magnetic flux is maximum. Because the circuit is rotating, okay, the magnetic flux is decreasing. Eventually, it comes to a point the magnetic flux is going to be complete, is going to be zero, exactly zero. Past this point, the circuit is going to be a little, the magnetic flux through the circuit is going to start increasing, and you're going to start seeing the circuit all over again, right? Magnetic flux increase, see? Magnetic flux increase until it reaches a maximum value. So that was the smart way that people figure out to create a simple device, the simplest possible device. I'm going to do the following. I'm going to get this guy here. Okay. Send to back. Yeah. Good. Like that. Okay. So here you go. Here's the magnetic flux. Initially, it decreases, right? Then it becomes zero, and then it increases. The area vector of the circuit at this very instant of time is going to be pointing in this direction, right? Which is perpendicular to the magnetic field. Anywhere else in between, the area vector is going to have an angle between 0 and 90 degrees. Anywhere else in between. Did you get the idea? And let's take a look at the internet. Here you go. It's going to be generator experiment. YouTube. Okay. Electric power, let's see, experiment free, no, not free energy, Van de Graaff generator. Should a person touch the science project? Let's go to YouTube. I'm not getting a good hit here. Generator. Demonstration. We have a generator there at the college. Oh yeah, here you go. We have this one there at the college. Exactly this demo here. Skip. What's up?
Hey, Jared. We brought you here today to.
You can buy
Here you
a
go.
generator for your.
Here you go. Here's the generator. Here's the light source. Here's the crank that I told you. Okay. And what this crank does, it rotates a circuit in a magnetic field that's in a magnet that is right here inside this box. Okay.
Bicycle where you attach a small, looks like a little motor, and then there's a little wheel that spins against the side.
Have you ever seen this generator of a bicycle? When I was growing up in Brazil, we used to have those things. Okay. We would attach a generator to the wheels of the bicycle. The friction of the wheel would make a circuit rotate in a magnetic field, and that magnetic field would generate a current that would power a light bulb. And that's what this guy is talking about.
Side of your tire and generate electricity to power your light at night, your bike at night. And nowadays they don't worry about these fancy ways of.
Yeah, they don't worry about this fancy way anymore because we can use batteries. Okay, we use LED lights. LED lights doesn't consume as much electricity from the battery, so you don't use those generators in the bicycle wheel anymore.
Generating electricity, but in the old days, that's what we used to do. This is also a generator. I'm going to turn this crank and generate a current in this.
Okay, so the magnet and the circuit is right here inside. Okay, when you crank this guy up, the circuit is going to rotate about inside the magnet. And the circuit has some wires that comes out from this box. You connect to the light bulb, and the light bulb is going to flicker.
In this bulb.
Here you go. And this current, it changes in time. Did you see the simulation there? Let's go back to the simulation. Do you see how the current, not just the current, but the voltage changes in time in a sinusoidal fashion? So if you go ahead and crank up uniformly, okay, the circuit uniformly with constant angular velocity, you do generate a sinusoidal voltage, a voltage that changes in a sinusoidal fashion, as well as the current. And that's the principle of the AC circuit. That's the principle of the AC circuit. The current goes back and forth in the circuit. Okay, so just try to visualize the current in, for instance, the DC circuit, the direct current circuit. Direct current circuit, the current just oscillates in a single direction, either clockwise or counterclockwise. In an AC circuit, which when in an AC circuit, the power supply is the generator itself. In an AC circuit, the current goes in one direction and then reverse direction back and forth at a given frequency. That's the important difference between a DC circuit and an AC circuit. The change in voltage is sinusoidal because we are cranking this device here at a constant angular velocity. Okay, if the angular velocity weren't to be constant, then the voltage would change differently. So let's go back to the demo.
Okay, so what's happening here? This is actually hard to turn, and the reason is that there are coils of wire in here and magnets, and there's a change in flux in the coils of wire that is produced by the turning motion of the coils. And through Faraday's law, the change in flux through a coil of wire generates a current in the wire. And that's the current you see in the bulb here. So a generator, there's one of these in your car. It's called an alternator because it has some extra gadgets, but at the very heart, it's a generator. You've got the motion of your wheels of your car that generates a current that charges your battery.
So that's the, and let's take a look at this illustration here as well.
Provide electricity to thousands of houses around the city. They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be...
That's a hydroelectric power. That's how we generate electricity with a hydroelectric power. But another way of doing the same thing is by using an internal combustion motor, right? That's going to put this turbine to rotate and generate electricity as well, but not with the water, but with diesel or gasoline engine.
We fit these...
Another way is to use wind power, right? The wind comes by these propellers, make the propeller rotate. The propeller rotates a circuit, and by electromagnetic induction, it produces a current. That's another way.
Giant windmills, and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field.
And
As the
rotate.
turbine rotates, the coil starts rotating.
That's a nice illustration because like it's a 3D illustration, right? Alright. Do you see the flux, the magnetic flux changing through this area? That's because the area vector is making an angle with the magnetic field vector. Okay, we can even go ahead and write down the equations for that.
And the wires start moving up and down inside the magnetic field that produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy.
See that the current changes directions? Okay, the moment that it changes direction, the current goes exactly to zero because the magnetic flux is zero at that instant of time.
Into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say in our example,
What it's going to do is the same thing that I did in my PowerPoint presentation, but using a 3D drawing, right? At this very moment in time, the flux, magnetic flux through the circuit is exactly zero because it's not passing through the area of the circuit, but it's just grazing the area of the circuit. The B field makes an angle of 90 degrees with the area vector. Okay, and let me go to my, here you go. This one right in here. The induction current. The induction current, the effect may be the opposite. We input motion to the system and the output is current, is electric current. Going back to our flux, magnetic flux, right? Now our magnetic flux, the equation is going to be slightly different. Let's not forget, it's going to be B times A times sine, not sine, it's cosine of theta. Cosine of theta. That's how it is, okay? BA cosine of theta. When the angle between B and A is zero, we have maximum flux. When the angle between B and A is 90 degrees, we have zero magnetic flux. Zero magnetic flux corresponds to this very instant of time, okay? That's zero magnetic flux. Now we put it to rotate.
Clockwise. Somewhat like this.
Okay. Now the magnetic flux is increasing. Magnetic flux increasing, then the current must rotate contrary to the external magnetic field. In this case, should be clockwise current, okay? Clockwise current, just do the right-hand rule. Okay.
Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this, such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire. That is the direction in which you're pushing the wire. The forefinger gives us the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards. So it'll be a great idea if you can first see whether you can try it yourself. So go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire.
Okay,
Oh,
so here you go.
yeah,
There's an
this
easier
way.
way, right? There's an easier way to do that. So here you go. Clockwise, counterclockwise direction. Counterclockwise direction. Okay. I don't like the way he did that here for the right hand rule. Okay, but just go ahead. You know, your thumb must point in the direction contrary to the magnetic field. And your hand, right hand, the palm of your right hand must rotate in the direction of the electric current.
It's out, it goes to that external circuit, maybe where there's a bulb. We'll look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating.
Until
Because you can see the pink wire is still going up and the blue wire is still going down.
the current continue flowing in this direction until you reach maximum magnetic flux.
Until
There you go, right in here, maximum magnetic flux. Now, from now on, the flux will decrease in time. It increased from that moment that the circuit was flat up to this point. And now that it reached maximum value, the flux is going to decrease and the current must change.
come to this point.
Okay?
Because now the pink wire starts moving downwards. And now the blue wire starts moving upwards.
Okay, now
Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up. This means now the current in the pink wire should be out of the screen.
yeah.
As we already saw using our right hand.
Now the current must revert direction, right? Because the flux is decreasing. Right hand rule, let's see, would be clockwise direction. Okay, and that's what I'm going to show you.
The current must be out. And in the blue wire, which is going up, the current must now be inwards.
Okay, right here,
Every
right
time
here.
our coil is in this position,
See,
which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this.
okay,
Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular.
okay. So let me put that in there so you can consult this one simulation, another simulation for the generator. I like this one. The only thing I didn't like it, I like the illustration. The only thing I didn't like it, the explanation of the right hand rule. He made it very complicated. Okay. Mathematically speaking, you know, the equation goes like that. Because the circuit is moving with constant angular velocity, we can change the theta to omega t. Okay? We can change the theta to omega t. Because the flux changes in time, we must have an induced current. We are not going to get into the detail. Don't forget this equation goes right in here. What is that? Right in here. In Faraday's law. Okay, so this term goes right in here. And now it's a little bit difficult to continue the derivation because it requires differential calculus, okay? BA are constant. What's not constant? So because BA is constant, we can take it out of this delta term. And we are left with this term here. Delta cosine omega t, delta t. Well, it's you know, when you do this delta cosine omega t delta t, you get something like that. I'm going to give you the answer. Okay, you don't have, it requires, like I said, it requires calculus to come up with this answer. And not only we have sine of omega t, but we have also minus sine of omega t. This negative sign cancel out with the other negative sign. And we end up with this relationship for the current. And that's what we call an AC circuit. An AC circuit is a current that changes in a sinusoidal fashion. Okay? That's the principle. That is the principle of an AC circuit. A current that changes either in a sinusoidal, or sinusoidal fashion. Sinusoidal fashion. Okay. And it's 10:12 already, right? We can, let me take attendance. We're going to take our break and then start our what before, let's see. Let me take attendance here first, and then I will let you know today is the 27th. Insert should be lab 5. Is it lab 5? Yeah, it is, right? Lab 5. Right in here. Jacqueline, are you there, Jacqueline? Okay. Thank you, Jack. Next is Sky. Sky is here, right? Just say hi, Sky. I don't hear it from Sky. Okay, I'm gonna put a star here on her name. Hopefully she'll come back. Ashley, are you there, Ashley? I don't see Ashley. Next is gonna be Corina. Hello, Corina. Oh, Sky is in there now. Corina is also here. Next is Norberto. Norberto here. I don't see Norberto. Vanessa Mena.
Here.
Thank you, Vanessa. Yorgo. Yorgo didn't show up today, yeah? Okay. Yorgo is not here either. Lizelle. Okay. Next is gonna be Paul. Paul Zapata. Okay, 6 students, 7 here. Okay, 10, 14. Okay, let's go take our break. When we come back from the break, I'll tell you what we covered so far. Break from 10:15 to 10:30 a.m. After the break, I will tell you which sections of chapter 22 we covered so far. Okay, I'm putting this note here for myself, so I don't forget to tell you that. And if you arrive late, right, don't forget the exam is gonna be next Wednesday. Oh, wait a minute, Wednesday after the spring break, and those are the sections. That's the material for exam 2, labs 1 and 2, related notes and videos. And I'm going to put that other video in there that I like.
Buy
Here you go.
a generator for your bicycle.
That's another video. Okay, 3 videos for the generator. Oh, that's the electric motor. That's not the generator. Let's go back to, let's see, this one. This is the generator. Just correct it here. Okay, don't forget that's the electric motor. This one is the generator. Generator right here. Okay. I'll see you in 15 minutes. I'm back here. Okay, so let's take a look what we covered so far. I'm wondering whether we should do the lab now. Let's see, we have only 7 students. There are 2 students missing now, right? Let's see, Norberto. Are you there, Norberto? Norberto,
Yes.
right? Okay, and then who else is missing? Ashley is missing, and Yorgo is missing. I wonder if we should do the lab 5 today, but I'll be deciding that the next few minutes. These 2 students are missing, maybe we should do lab 5 another time. That's what I'm thinking here. But let's take a look what we have covered so far in chapter 22, right? Right here. Chapter 22, induced EMF and induced current. Chapter 22 so far. Chapter 22 so far. 22.1, induced EMF. EMF stands for electromotive force and induced current. Let's see. Family, okay. Okay, electromotive force. Electromotive force and induced. I don't like the word electromotive force, by the way, but that's what they use it. It's not like a force, it's more like an energy, okay? Potential energy. And then I cover motional EMF. Electromotive force. We talked about magnetic flux as well, just like we talked about electric flux before. And Faraday's law of electromagnetic induction. Let's see what they covered that. Okay, so here you go. Everything that I have already covered, right? The magnet approaching the coil, right? And generating a current in this coil. Why do we use a coil? Okay, there's a reason why we use a coil. For practical terms, we do use a coil. We don't use a circuit with just one turn. Okay, we can induce a circuit, a current in a circuit with a single turn, but in practice, we do not do that. We use a circuit with several turns, because for every turn that we add to the circuit, we have this multiplicative factor, right, in the current. So if you get, for instance, a current of 1, whenever you use a circuit with just a single turn, a circuit with 2 turns will generate a larger current, twice more, because it has 2 turns. A circuit with 3 turns would generate a correspondingly larger current of value 3, and so on. So it's like an amplification factor. Each turn in the coil results in an amplification factor. If you come up with 100 turns, like many coils that we find out there, you're going to have an amplification factor of 100. Okay? And like I said, this is the inductor. This is the inductor that I have talked to you before. And go, this is what? Induced EMF lies at the heart of the automobile cruise control, in which an EMF is induced in a sensing coil by magnets attached to the rotating drive shaft. Okay, so okay, that's another way of we are changing the magnetic flux by making this wire in the circuit oscillate back and forth, right? So we are changing the area of the circuit. That's another way of changing the area in the circuit and generate an electromotive force. In this case, because the area is increasing and decreasing, you are also generating a AC current here. You're also generating AC current here. Okay. Motional EMF, we did that. Okay, 22.5. 2.5 motional EMF. Okay. 22.5. Figure 22.6. Let's see, section 22.6. Where is that? Oh, wait a minute. Emotional EMF. Let's see. Oh, it didn't go. I'm looking for 22.4. Getting a little bit lost here. Let's see. 22.4. 22.4, Faraday's law of induction. Okay, that's the one here. Okay. Oh, that's one other application of electromagnetic induction. Have you heard of the induction stove? Right? So it's an interesting concept. You know, if you want to warm up your food or your water, you don't need to turn on the fire in the, or even the resistor. You use an induction stove in which you can touch the surface and it's not hot. It's not like those stoves that you have a very large resistance that becomes hot, right? In the induction stove, how does it work? In the induction stove, let's take a look here. Okay, 2 pots of water that were placed on an induction stove at the same time. There are 2 interesting features in this drawing. First, the stove itself is cool to the touch. Second, the water in the ferromagnetic metal pot is boiling. Okay, so the pot is made of a special type of metal that is ferromagnetic. Those ferromagnetic, we didn't cover, you know, those types of metals, okay? But there are different types of metals, ferromagnetic, diamagnetic, and so on, that behave differently with respect to the induction. The ferromagnetic metal is used to boil the water. Okay, whereas the other one is not, the other metal, the other pot is not made of a ferromagnetic metal, okay? The key to this puzzle is related to the fact that one pot is made from ferromagnetic metal and the other is from glass. It's not a ferromagnetic, it's made of from glass. So one is a conducting metal, the other is not a conducting, one is a conducting pot, the other is not a conducting pot, right? We know that metals are good conductor, while glass is an insulator. Perhaps the stove causes electricity to flow directly to the metal. This is exactly what happens. The stove is called an induction stove because it operates by using electromagnetic induction. So what's happening here? The stove induces a current in the metal pot. And the metal pot alone becomes warmed up, heats up, okay? Because of the current in the pot, it warms the pot only, not the surface of the stove. Just beneath the cooking surface is a metal coil that carries an AC current, 25,000 hertz, 25 kilohertz or 25,000 hertz. So now just below, right? the cooking surface, we have this AC circuit. AC circuit that induces a current in the metal pot. This current produces an alternate magnetic field that extends outward to the location of metal pot. As the changing field crosses the pot bottom surface, the EMF is induced. Because the pot is metallic, an induced current is generated. The metal has a finite resistance, okay, to the however, and heats up as energy is dissipated in this resistance. The fact that the metal is ferromagnetic is important, okay? So what's the importance of ferromagnetic materials, okay? It contains magnetic domains, and the boundaries between them move extremely rapidly in response to the external magnetic field, thus enhancing the induction effect. A normal aluminum cooking pot, in contrast, is not ferromagnetic, so this enhancement is absent, and such cookware is not used within the induction stove. EMF is also induced in the glass pot and the cooking surface. However, these materials are insulators, so very little induced current exists within them. Okay, so even though it's an insulator, there is still some electric current induced in the glass pot, but it's so small that it's not enough to heat up the pot. Same thing, the aluminum pot also the aluminum pot also experiences an induction current, but it's not as efficient as that of a ferromagnetic metal pot. Okay, and that's how one of the applications of Faraday's induction. So we cover Lenz's law. $22.5. Let's say 22.6. Okay, that's another example of how you can induce a magnetic field in this loop, right? So what's happening here? We have a magnetic field restricted just to this area. If this ring is at this position, there is no magnetic flux whatsoever. As it falls, eventually it's going to be at this point, the magnetic flux is still zero, right? But then as it enters the magnetic field region, the magnetic flux increases. Okay? When the ring is exactly here at this position, the magnetic field came to its maximum, the magnetic flux came to its maximum and becomes constant until it reaches the bottom part, the bottom area of this region of magnetic field. And then the flux decreases, okay? So we are going to have an induced current, from here, all the way up to here, all the way down to here, and from here all the way down to here. At this point, the magnetic flux increases. At this point, the magnetic flux decreases. Okay. And applications of electromagnetic induction to the reproduction of sound. I'm not going to cover that. Okay, 22.6. Electric generator. How to generate? Oh, okay. So we did that, right? A generator. How is it? Electric generator. So he goes through. Here you go. Here we have turbines here, right? Electric generator. Let's see if they have a nice. Oh yeah, here you go. The same drawing. The same drawing. The circuit subjected to a magnetic field. But then now you rotate the coil by mechanical means, either by attaching a internal combustion engine to the shaft, right? Or by hydroelectric power, which converts the potential energy of the water at one height into kinetic energy of rotation. Oh, you can do with your hand as well. Okay, different ways of. But remember, we don't use circuits just a single coil. Okay, in practice we don't do that. In practice we use a circuit with several coils, but they represented just a single coil here to make the drawing simpler to understand. Okay, that's all. And here you go, the sine of theta that I told you, right, folks? Sine of theta, the theta is going to be omega t. Here, that's what happens with the voltage. The voltage behaves in a sinusoidal fashion. Okay, and mutual induction. We didn't cover that yet. Okay, let me put that mutual 22.8 mutual inductance and self-inductance. We're not gonna cover that. Yeah, let's not cover that. Oh, no, we have to cover that. Sorry, we have to cover that. And let me put this, bold face here. How we're gonna do also transformers. Whatever is in bold face, we didn't cover yet. See, we have transformers right here. And we have two more sections to go for this chapter. 21, 22, electromagnetic induction, right? Transform. Okay, so we have two more sections to go. This one we already covered, the electric generator. And 10:45. Let's see what we're going to do. Yeah, let's have our, let's have our lab today. Okay. So you don't get too burned out with this material. But see that we cover a lot already, right? In chapter 22. We covered a lot in chapter 22. And let me get my notes for lab number 5, and we started lab 5. Download spreadsheet. Okay, lab 5 is not much different from lab 4. Okay, and I'm going to upload lab 5 spreadsheet to your lab report, raw data, lab 5. Let's make sure everything is in. Oh, some of the reports have a graph there already. I don't want you to have, I don't want it to be like that. Let's see. Okay, this one is good. This one is good. R1, R2, two resistors. That's good. That's good. Good. Yeah, that's good as well. No problema here either. No problema here. Okay, the only problem is this one here. Okay, yeah. This one's number 10. And we are done. And I will upload that for you. Group 1, spreadsheet. Group 2 is spreadsheet. Group 3 is spreadsheet. And what I'm going to do, let's take a look at some other simulations that I have here. You know, it's going to be very useful for you to understand the experiment. Fat simulator. Okay. So fat, here you go. No, I don't want that. That's Portuguese. Let's see if they have English here. Maybe I go here. Okay. Physics. Okay, let me copy and paste the link to the simulation. You might want to play a little bit with this thing. Another good link. Another good link for physics simulation. Okay. This one. Save it. And we want physics. And motion, sound waves. We don't want sound waves. We don't want working energy. Let's see, electric circuits. That's what we want. Right? They have a bunch of electric circuits simulations right here that allow you to visualize what happens whenever a current is created in a circuit. We see AC circuit, and DC circuit. I recommend you to look carefully on that. Here you go. This is what we have. We can construct a virtual circuit with this simulation. First with the C circuit. Let's take a look at this C here. Okay. So we're going to start building our circuit in the same way that we build the experiments of our labs, right? First with the battery. Here's the wire. Very simple, very simple. We have all sorts, by the way, we have all sorts of computer programs out there that are far more involved than what you see here, okay? And they allow people like electrical and electronic engineers to construct electronic circuits. Okay, wire, and then we have our resistor. See a resistor here? We can even change the resistor. Let's see. Oh yeah, we can even change the resistance of the resistor. And I want to put also a switch. I didn't put a switch. Yeah, I can put it here. Okay. And then I'm going to close the circuit. Those are just our regular wires that has negligible resistance. That's what we did in the previous lab, in lab number 4. One resistor, one battery, and by the way, see, we have voltmeters and ammeters here. See that? When I close right now, do you see the electric charges here? The negative electric charges. Those negative electric charges, they are at rest right now because the circuit here is open. It's not closed. Okay, and I can switch from electrons to conventional direction of the current. Okay, but let's do with the electrons first. I'll close this circuit. Oh, I'll close this circuit, and now you see the electrons flowing from the negative polarity of the battery towards the positive polarity of the battery, right? If I change here in this window for the conventional direction of the current, you're going to see that the current is going to flow in the other direction, the clockwise direction. That's the type of picture that you have to have in your mind when you put together electrical circuits, okay? And then I'm gonna get my voltmeter and measure the voltage here. See, this battery has 9 volts. Yeah, I put it as a 9 volts. I can put 10 volts like we did before, but because I inverted the polarity here, we see that that's the positive polarity of the battery. I am touching the negative, the black probe of the voltmeter in the point where we have the positive of the battery. He's giving us this negative voltage. So if I want a positive voltage, I have to swap, right? I have to, like that. Yeah. Now we have a positive 10 volts. I don't like that. Let's do differently. Here you go. Yeah, okay. Now we can see voltages in voltmeter in parallel. Let me decrease a little bit here, right? So I have space for my voltmeter there on the top. Okay, now we go positive, negative, 10 volts. If I swap the probes, I get a negative, right? So that's how we measure voltage. If you want, we have to connect the voltmeter in parallel. That's what we did in lab number 4, right? If you want to find out the current in the circuit, we have to connect my ammeter in series. Okay, I have to break the circuit, connect it here, and okay. I don't like it because it's crooked here, but let's see. Let me break it. Why? Okay, now I can get it straight. Okay, straight. More wires. One more. I'm gonna increase, yeah, the distance a little bit more so I can put another wire right here. Oh. And now my ammeter is measuring the current through the circuit, right? My voltage is not showing the voltage because the probes are not connected, but if I connect, here you go. What happens if I remember the current here through this ammeter, 0.71. What if I change the voltage in the battery, right? I'm going to increase the voltage. What do you think is going to happen to the current? V equal to Ri, the current should increase, right? I increased to 92 volts, from 9 volts to 92 volts. And now look at the current, much stronger. I decrease the current, okay, 2 volts. The motion of the charges is lower, right? 2 volts right here. And now let's do the experiment of today. The experiment of today, we're going to do the experiment. First, we're going to do the experiment here, and then we go back to our spreadsheet. The experiment is going to, I'm going to take out those cables here for now, okay? And I'm going to move away my, yeah, make things. The switch can be anywhere, can be before or after the resistor. Okay, if you feel confused with the switch being after the resistor, okay, I can put it before the resistor, but it doesn't matter. Doesn't matter where the switch goes. Resistor 1, right? And then we're going to put a second resistor in our circuit. Resistor 2. Preferably should be resistors of different values. Preferably. This resistor is 10 ohms. This resistor is what? 14 ohms. Do you see the color code? Right? You can find out what is the resistor value just by looking at the color code. This should be number. This should be 1. This should be 4. This should be 1. No, this should be 0. Black is 0. And then we have the color code for the tolerance of the circuit. So that's what the circuit is, right? And we usually do all the way up to 10 volts only. And what about our resistance? What's the highest one you can go? You can go at most 120 volts, 120 ohms. This one is 13, the other one is 10. Okay, that's good. And let me get all my stuff here. Let's see, 4 single resistor. Let's see, what about 5? Nope. So single resistor, let's see if I, that's what we did last time. I don't want a single resistor, I want a double resistor. And I am going to get it now. Resistor, single resistor, okay. Open. Single resistor in series. Okay, here you go. Here is my, what's the first thing that we're going to do in this experiment, right? I gotta open. Here you go. My spreadsheet. Okay. The first thing that we do in this experiment, I provide you use 2 different resistors, and you go ahead, you measure the resistor with the multimeter. Just you close that here as well. Here you go. You know, you get with the multimeter, digital multimeter. It's a different type of multimeter. They have that, okay? Okay, resistance measurement, adjust the multimeter to measure resistance. We have the jacks here. Black banana termination to blackjack. Clamp red alligator to one end of the resistor. Clamp black alligator to the other end of the resistor, right? Something like that. That's how you measure the resistance of the resistor. Okay, and then you log the resistance values right here. Okay, one resistor here, another resistor here. This one is 346, this one is 220.5. Don't forget the units of resistance. Okay. And forgot to spell out here, right? Lab 5, Ohm's law. Ohm's law with 2 resistors. Okay. And don't forget before that, right? Upload the report for lab 4. Report for lab 5 is due. Let's see, when is it due? It's going to be due after the exam. So it's going to be due on 17th of April. It's due on April 17th, okay? Lab 5 is the one they're doing today. So the materials for Lab 5. The objective for Lab 5 first, right? Verify Ohm's law, just like we did for a single resistor. Now we're going to verify Ohm's law for 2 resistors in series. And the materials are the following: 2 resistors, resistor 1 and 2, that you have to measure the resistance with a digital multimeter. 2 black cables with banana termination, 2 red cables with banana termination. 2 alligator clips, which we use to measure the resistance value. Okay, and I still didn't introduce the other 2 devices, but then I'm going to start with the procedure. Here you go. Procedure. Measure the resistance of each resistor with the DMM. And then we have a power supply. Right? You already saw here the values of the resistors measured. Here, how you do is the multimeter. And now we are going to use a power supply. Start with the power supply. That's the one. You're also going to need a proto board to connect the resistors. So let's take a look at the proto board, how they look like. This is a very useful device. This is a very useful device to build circuits. This is mass manufacturers. They sell for peanuts out there, okay? Let's take a look. Proto board. Proto board means prototype board. Prototype board. Perforated. Let's see, I don't want those. That's not the one I want. Let's see. Nope. Perforated circuit board. Oh boy, where is it? Is that the one? Let's see. Nope. Unfortunately, for some reason they're not showing the board. Maybe this one. Anybody here likes to play with electronics, by the way? You know, there are some of my students, they like to play with electronics and they know exactly what I'm talking about. But let's see. Plastic protoboards. Plastic protoboards. Okay, that's what I want. Okay, that's one protoboard that you're going to see out there. You see, they're made with those holes here, several holes here inside, so you can connect resistors more easily. Not just a resistor, but any other component like capacitors as well. Resistors, capacitors, transistors, inductors. Okay. And they're very useful. I bought a bunch of those when I was playing with electronic circuits. Nowadays, I don't do that anymore. I just hire people to do the electronic circuits for me. They have small proto boards like this one that you saw. $9.08. Oh, it's not $9, 9 Brazilian dollars, right? US dollars, but this thing is like $2. $2, maybe it's cheaper than that. They are mass manufactured. Okay, let's see. Yeah. And that's how they look like. Protoboard. And I also produced the protoboard. Here you go, power supply, cable. We're going to build our circuit just like this one here that you saw in the simulation. Where's my simulation now? This one, okay? Battery, right? 10 volts, let's put 10 volts here. Yeah, 10 volts we have here. And then the cables. One cable coming up from the positive side of the battery. Resistor 1 in series, resistor 2, and here is my product, the protoboard that we have there at LA Harbor. It's a larger one than that one that you saw in the internet. All those holes here, they are used so we can connect our resistors more easily. Since I'm connecting the resistors in series, one end of one of the resistor must be in the same column of the other end of the end of the other resistor. Okay, so that's the protoboard here that we're supposed to have more holes in the other part. And let me see, I can do that here. I didn't do that before because of just too much work, but now I can do it. Let's see, now that's not what it is. Okay, a little bit higher. Good. Oh, no. Well, position it properly. Yeah, a little bit more, right? A little bit more down. What about now? Not yet. Yeah, now we have it. And we're supposed to have holes here as well, but I'm not gonna draw them, okay? Connecting one resistor in series with the other resistor, and then we close the circuit. That's the diagram, that's the circuit diagram that we have. This thing is the same as this thing here. Of course, this one is a simplified drawing of this one, which, by the way, is the same as this one that you see here. The only difference that this one has a switch that the other ones don't have. Okay. If I want, it doesn't matter if you put your resistor here in this arm or if you put the resistor in the other arm right here. Doesn't matter. You get exactly the same result. Okay. Whether the second resistor is in the horizontal or vertical direction, you still get the same result. Like that. Close the circuit, the current flows from negative to positive across the battery and through the other resistors. Make something nicer here. Oh, I need to cut this wire. I'm gonna do like that. Okay, here you go. Okay, current flowing through the circuit. I open. Oh no, that's not what I want. Yeah, going back. Here you go. If I want to open the circuit, current stops flowing. Current stops flowing, right? And what we're going to do now? Now we are ready to start the experiment. 11:15, yeah? Let's see, we're gonna here you go, set the power supply to 10 volts. Okay. Set the MM to read DC volts. Measure V total. What do I mean by measuring V total? I go ahead, get my digital voltmeter, and I connect between those 2 points right here. Okay, here you go, 1 point and the other one. And that's how it looks like in a diagram. We can do the same with our simulation. Get my voltmeter here. I want to put here. I don't know. Yeah. Those 2 points. Why 0? Okay, it's 0 volts because the switch is closed, is open. Once I close the circuit, it's gonna read 10 volts. Okay? And that's what we're doing. Let me change. Okay. We set it to 10 volts right here. Let me change the color. And we measure the total voltage as well at 10 volts. That's how the procedure goes, right? Vary it from 10 volts to 2 point whatever. And then we invert the polarity. Like we invert the polarity. And how do we invert the polarity? In this case, we have to invert the polarity. We have to put the battery upside down. When we put the battery upside down, the voltage red is going to be negative, right? The voltage red is going to be negative. That's one way of reading the negative voltage. Disconnect everything and start from scratch. We're going to measure. And by the way, you know, there's more to that because we have to change the voltage. We did for 10 volts. We're going to do for 864 2.8, right? And invert everything and measure everything. And what does it mean? Going back to my, okay, so 10, we go back to 8 now, okay? So whatever I set here as being 8 volts, that's what he measured, right? You do that for positive and negative. 8, 6, 4, and 2.8. Oh, 2.8 is this one right in here. That's how we perform the experiment. We do that for positive and negative volt values. Okay. Step, we go lab procedure, plug the resistor, connect black cable, that power supply to 10 volts, set the MM to read DC volts, connect the MM in parallel to the two resistors, read voltage indication, everything, all the instructions are here. Invert cable of the power supply to feed the negative voltage to the circuit, reinvert the cables after the previous measurement. Okay, and then we start measuring the voltage across the first resistor. When we did the measurements according across both resistors altogether, you know, we obtain a voltage that coincides with the value of the voltage of the battery. But if we are going to measure just the voltage across the first resistor, let's reinvert. Here you go. Just across the first resistor. the value of the voltage is going to be different, 1.58. Remember that we're set that at 2.8 volts, right? 1.58 for 2.8 volts. If we increase to 4 volts, it increases to 2.26 and so on. Okay, 4, 6, 8, and 10. So what are you doing? We're doing this column right in here, V1, which is the voltage across the first resistor. We already did this column with this column here. Now we're doing this column with this column here. Okay. And now we're going to do this other one here. Okay, so that what here you go. Connect view R1, connect R2, close the circuit, and put the digital multimeter in parallel with the first resistor only. Okay, compare that with the previous circuit. Okay, that was the previous circuit, that's the new circuit now. Measuring the voltage across resistor 1 only. Okay, and let's take a look at our simulation. Okay, this is exactly what you're doing, right? Another way to invert the voltage, instead of inverting the battery, we just invert the probes here to give us a negative voltage. That's another way of doing that. So we did for everything, and now we're going to do for V2. Okay, V2. That's the negative, measure V2. Put together the circuit and connect the digital multimeter in parallel with resistor number 2. So we did in parallel with resistor number, we are going to do in parallel with the resistor number 2. We did it in parallel with resistor number 1, and we did it in parallel with both resistors. But now let's concentrate on that. Okay? Did I do that? No, that's resistor number 2. We start with positive. Okay. Notice that we are at 10 volts, and this guy here for V2 is marking a fraction of 10 volts. Decrease to 8, right? That's exactly what's happening in my spreadsheet. The numbers are not exactly the same, but that's exactly what's happening with my spreadsheet as well, right? 8 volts, 6 volts. Look at the voltage here across resistor number 2. 4 volts. Okay, 1.74 and 2.8 volts. Once we're done with that, we invert the polarity to get the negative voltage and start increasing it all over again to 4, 6, right? Negative voltage, see that? 8 and 10. Okay, so we are done with V2. That's V2 here. I'm going to put with the color blue. And now we have, those are all measurements. Those measurements that you see here, you get from the screen of the power supply. Those other measurements is from the DMM. And now we are going to measure the current. Okay, we're going to measure the current. I leave the current to last because it's the more difficult one to do. Negative, measure the current. Start from scratch. Power supply. Digital multimeter. First resistor, second resistor, close the circuit. Okay? We are doing only I plus. Before, in the previous experiment, we placed the multimeter here, and then we removed the multimeter and placed it here. Here, we're going to do only at this spot. Okay. And what do we do? And I'm going to go here to my simulation. I'm going to break my circuit, put my ammeter here. Okay, and it measuring the voltage. Now, if I want, let's see if I want to have a negative value, right? I have to invert. Let's invert this guy here. Let's see if we get a negative current. We repeat what we did before. Yeah, it's not showing a negative value here. Yeah, this ammeter doesn't have a polarity. That's why. But the ammeter that we use there, the ecology, that have a polarity. Okay, and we adjust this battery from 10 volts to 8. Okay. Notice that the current is decreasing. 6. Right? Oh, 6.26, 4. Look at the value, and 2.8. That's the procedure. That's the experimental procedure. Now I can put my voltmeter back there. And then, invert the polarity. If you're using the proper ammeter, you're going to see the negative current there. And that's what we do right in here. Note, see that those currents are negative. And by the way, V1 plus V2 must be very close to V total, okay? V1 plus V2 must be close to this. V1 plus V2 must be close to this one here, V total. What do we do next? Let's go to our notes. You have 3 graphs to plot. V total along the y-axis and I current along the x-axis. V total and I. Insert. You go. Straight line, trend line, R square, right? That's one. Then, which other? V1 and I. Okay, I will change this graph here to V1 and I. V1, I just click and drag to V1. Here you go. Now we get a different slope, right? And then we do that for V2 as well. 3 graphs. I will emphasize the fact, plot the following. Plot the following. A, B, and C. Okay? The slope of the first graph should be close to R1 plus R2. The slope of the second graph should be close to R1. The slope of the third graph should be close to R2. Okay. 11:30. So that's what the experiment is all about. What else you have to do? Fill up. I'm gonna put here. Okay. What else? Fill up the units in the table. Right. 27. Adjust the sig figs according to the table I provided you. Fill up the table for the last table. Fill up the slope. Should be before, right? It would be those three here. And determine the CL for each graph. And that's what it is. Okay, here, here, and here. Okay. Let's see how you folks are doing. 11:30, right? We need a little break. Let's take a little break. Otherwise, you're going to get, I'm getting burned out here as well. Let's take a break. 11:32. Any questions? This experiment is very similar to the previous one. The only difference is that we have two resistors. And now because you have two resistors, you have to measure the voltage across each resistor as well. The measurement of the current is going to be done only in one place because the two resistors are in series. Okay. So let's see how you're doing there before you go in our break. Let's see. 7, 8, 8. I want to hear from you. Jacqueline, did you plot the three graphs already, Jacqueline? Yes? Okay, good. And what about Sky? Did you plot the three graphs, Sky? Yeah, good. Next, Ashton is not here, right? Next is Corina. Did you plot the three graphs, Corina? Yeah, one more. Okay, Norberto, did you plot the three graphs? Yep, good, thank you. Vanessa Mena, did you plot the three graphs? Yes, okay. Any questions? Do you have any questions, Vanessa? Hello? Hello, Vanessa, do you have any questions? No? Okay. Next is gonna be Lizelle. You plot the three graphs. Is Lizelle there? Oh, yes, okay, good. And next is gonna be Paul. Okay, any questions, Paul? Next, none, okay. Slope. Slope, okay? So get the percentage difference. Okay, did you get the slope already? Did you get the percentage difference for the slope? Jacqueline? Not yet? Okay. Not yet, it's working on that, right? What about Sky? Did you get the percentage difference for the slopes, Sky? Still working on it? Okay, good. Next is Corina. Did you get that, Corina? Also still working, okay. What about Norberto? Did you get the slope the percentage difference for the slopes? Norberto? 1135. I can't hear from Norberto, but let's see. Need to plug into the table. Still, yeah, that's right. Need to plug into the table. Still working on it. Okay, so it's 11:35. Let's take our break, and then you come back for the remaining 10 minutes. Okay. Break from 11:35 to 11:50 a.m. Okay. Any questions? Okay, I see you in 15 minutes. Okay, I am back here. So let's see. 7 people. Okay, so how are you doing there? Let's see, Vanessa, right? Did you get to get the slope, Vanessa? The percentage difference for the slope?
Yes.
Okay, what are you getting there? How much percent are you getting?
For the V1,
Yeah,
I got 1.0129.
1.0129, and the other?
And then for V2, 0.4124.
Okay, and the V1 plus V2, V total?
1.06.
Okay, so it's good, right? And small value, so that's good. Lizelle, did you get the percentage? Thank you, Vanessa. Lizelle, did you manage to get the percentage difference for the slope? Hello, Lizelle. Okay, I can't hear anything from Lizelle. Let's go for Paul. Paul, are you there?
Yes, I'm here, Professor.
Okay, what did you get for the percentage difference of the slope?
I got 1.03 for V1,
Okay.
and then for V2, 0.52,
Okay, and what about
and
the
then
total?
total 1.06.
1.06. Okay, that's good. So thank you. So we've seen the values that we expect, less than 5%, close to 1%. Let's see, Jacqueline. Jacqueline there. Did you get the percentage difference for the slopes, Jacqueline? Okay, so let's see, checking game. I got the same thing as Paul. Oh, okay. Group 1 and 3, huh? Oh, yeah, you're the same group, right? So it makes no difference. Okay. Yeah, okay. Thank you, Jacqueline. What about you, Sky? Did you get the percentage difference for V1, V2, and V total? Hello, Sky, are you there? Okay, let's go for the next student here. It's gonna be Corina. Are you there, Corina? No, Corina left, huh? Okay. I'll put here star, and I'll put Corina. Apparently, she left. Next is Norberto. Hi, Norberto. Are you there? I got the same. Ah, yeah, you got the same for Vanessa, right? Because you're in the same group. Okay, that's good. Okay, and did I let me make sure I got you the link for that simulation. You know, that simulation that I showed to you is pretty good because it can help you understand better circuits, and not just you can have resistors there, but let's see here. You can also put, let's see if I can find here. You can put capacitor. No, you don't have capacitors here. Okay, so if you, let's go back to the home page right in here, right? Let's go back. You already have the link for the home page of the simulation. I encourage you to play a little bit with this site. Remember, we want the physics simulations and the electricity and magnets and circuits, right? So here, look at the simulations that we have. We have a total of 1, 2, 3, 4, 12 total simulations. Okay, here DC circuits, and here is AC circuits. Okay, here we have capacitors. You can learn about capacitors as well. And look at this DC circuit. There are two DC circuits, two different DC circuits, right? Two different, no, more, even more. So this one here, and play a little bit with it. Some of them have capacitors in there. Okay. And here go lab. This one we just did. Unfortunately, this one doesn't have a capacitor here. Yeah, I wish they had a capacitor. Yeah, it doesn't have for some reason. And but the other ones with AC circuits, they do have a capacitor there. Let's go back. This one has a capacitor, and this one has a capacitor as well. Here you go. See, capacitors right in here. And you can have DC circuits because you have a battery. Ah, okay, this one is more complete, okay? The previous one that we're looking had only the battery, but this one has not just the battery that you can build a DC circuit, but you also have an AC voltage that you can build a AC circuit as well. Resistors and capacitors, even inductors, okay? So play a little bit with that, see how those things work. It's 11:58 right now, and there's more things that we have to do in this lab, in this spreadsheet, okay? Make sure you get, make sure, I'm gonna write that down here. Make sure you get the sig figs. Already did that. Oh, I already wrote it here. Here you go. The sig figs, and submit this lab report on what, 1, 2, 3 weeks from now. 3 weeks from now, okay, lab 5. Do you have any questions? 11:59, we can stop here, and I'll be online for the office hours if you need any help, okay? Thank you for being here, and see you in 2 weeks after the spring break. Have a nice spring break vacation, right? Menos 25. Welcome, Vanessa.